Hello everyone, and welcome to today's presentation. We're going to explore the objective of multiplying monomials and polynomials. Our focus will be on multiplying two monomials, as well as multiplying a polynomial by a monomial. We'll also look into the concept of multiplying by monomials in general. This is the first slide, so I just want to give you a quick overview of what we'll cover today. I'm excited to get started, so let's dive into the topic. Let's talk about how we can model the multiplication of two monomials using a rectangle. Think of it this way. The factors, or the numbers we're multiplying, become the length and the width of a rectangle. The area of this rectangle then represents the product of the two monomials. For example, if we multiply 2x by 3x, we assign one factor to the width and the other to the length. So the width is 2x and the length is 3x. When we multiply these, we're essentially finding the area of the rectangle, which gives us the product. Now, to help visualize this process, we use algebra tiles. These tiles make it easier to see how the multiplication works out in a geometric way. By modeling the factors as tiles, we can see how their combination leads us to the product, reinforcing our understanding of monomial multiplication. This approach connects the algebraic process to a visual and tangible method, making the concept clearer and more intuitive. All right, let's take a closer look at this diagram. We see that the rectangle is made up of 6 square tiles. Each of these tiles has an area of x squared, which means that if we measure one side of a tile, its length is. When we add up all these tiles, the total area becomes 6 times squared. Now, notice how we can also express this area as a product of two binomials, 2x and 3x. Multiplying these together, we get 6x squared, which matches our total. This is a simple yet powerful way to understand how the area of a rectangle can be broken down into smaller parts and then combined through multiplication. So the key takeaway here is that counting the individual tiles helps us see how the total area is composed, and expressing it as a product shows the relationship between the dimensions and the area. This concept is fundamental as we explore more complex shapes and their dimensions throughout this presentation. Let's walk through this example to see how we multiply two monomials step by step. We start with minus 3x2 multiplied by 8x5 to make it clearer. We break it down into parts. First, multiply the coefficients, which are an 8. That gives us. Next, we multiply the variables, which are x2 and x5 since the bases are the same. We keep the base and add the exponents. So 2 plus 5 equals 7, making it. Putting it all together, we get minus 24x7. Remember, the key points here are: first, multiply the coefficients; second, multiply the variables; and third, add the exponents when the variables have the same base. This process is essential because it helps us simplify and work with algebraic expressions efficiently. And as a quick reminder, the rule am times n equals am plus n, which is exactly what we're applying here, adding the exponents when multiplying like bases. Now let's look at how we can model the multiplication of a polynomial by a monomial. In this example, we're multiplying 2x by the binomial x plus 1. Think of it like this. The width of our rectangle is 2x, and the length is x plus 1. When we find the area, it represents the product of these two expressions, which is 2x times x plus 1. Using algebra tiles here is very helpful. It allows us to visualize how each part of the monomial interacts with the binomial. The key idea is that multiplying a polynomial by a monomial scales each term, and the algebra tiles help us see this clearly. This approach is especially useful because it connects algebraic expressions with a visual, tangible representation. It reinforces the concept that the area of the rectangle corresponds to the product of the two expressions, making the idea of polynomial multiplication more concrete and intuitive. All right, let's look at what this model shows us. We have two x squared tiles, which represent the term 2x2, and 2x tiles, representing the 2x term. When we add these together, we get the total area as 2x2 plus 2x. Now notice that we can factor this expression by taking out the common factor, which is 2x. When we do that, we're left with x plus 1. So the entire area can be written as 2x times x plus 1. This visual helps us understand how the distributive property works in algebra by breaking down the expression into parts that are easier to see and manipulate. It's a great way to connect the algebraic expression with a visual, tangible model. So, by counting the tiles and grouping them, we're essentially confirming that the factored form matches the expanded form, reinforcing this important concept. Let's look at this example to see how multiplying a polynomial by a monomial works in practice. We start with 2y times the polynomial in parentheses, which is 3y2 plus 9. To do this, we distribute the 2y to each term inside the parentheses. So, we multiply 2y by 3y2, and then 2y by 9. When we multiply 2y by 3y2, we get 6y3 because we multiply the coefficients 2 and 3 and add the exponents of y, which are 1 and 2, giving us. Next, multiplying 2y by 9 gives us 18y, since 2 times 9 is 18, and y stays as it is. After that, we write the terms out. 6y3 plus 18y. Notice how we simplify the exponents in the first term to get the final answer. The key takeaway here is that when multiplying a polynomial by a monomial, we use the distributive property to multiply the monomial by each term inside the parentheses, and then we simplify the resulting expressions. This process helps us handle more complex algebraic expressions efficiently. Now let's look at how we find the area of this rectangle. We've already calculated the expression for the total area, which is 6x4y3 minus 2x3y4 plus 10x4y2. To write an expression for the area, we need to think about multiplying the dimensions of the rectangle. Remember, the area of a rectangle is found by multiplying its length by its width. So, in algebraic terms, we're essentially multiplying two expressions that represent those dimensions. This example highlights how algebra can help us understand and calculate areas, especially when the dimensions are expressed as algebraic expressions rather than just numbers. By multiplying these expressions, we're combining the factors to get the total area, which is a key concept in understanding how algebra and geometry intersect. Now let's look at how we find the area of this shape. We start with the expression 8x times 5x squared plus 9x minus 12, and then add 2x squared plus 3. To find the total area, we use the formula for the area of a trapezoid, which is 1/2 times the height times the sum of the bases. In our case, the height is 8x, and the bases are the expressions inside the brackets. So we multiply 2 by 8x, and then by the sum of 2x squared plus 3, and 5x squared plus 9x minus 12. When we combine those, we get 7x squared plus 9x minus 9. Multiplying through, 2 times 8x gives us 4x, and then we distribute that across the combined expression, resulting in 28x cubed plus 36x squared minus 36x. So the final expression for the area is 28x cubed plus 36x squared minus 36x. This illustrates how we can use algebraic expressions and the trapezoid area formula to find the total area efficiently. It's a good example of applying these concepts to more complex shapes.